Good afternoon, class. Can you give me a thumbs up if you can hear me okay? Okay, I also want to see whether all of you are actually really here. Okay, good. No? I have a lot to discuss now. As I mentioned, I'm not going to be able to cover all of the material that is present in the notes that were released through UVLE. So this is a supplementary lecture, so I'm only going to cover the parts which I think are the most important. So it is your responsibility to go over the notes and to take a look at them and study them. So this is really just additional instruction for you. Before I proceed, are there any questions with regard to the subject matter which I presented last time? Any questions? Okay, so if there are none, let's proceed. So just a short review of what we took up last time. Just spend a few minutes to take a look at to have this review. Okay. So last time we talked about an intrinsic semiconductor. An intrinsic semiconductor is a pure semiconductor. That means that it's not mixed with any other element. And the most common semiconductor that is used nowadays in electronic devices is silicon. So silicon has 14 electrons. This exists in 3 shells. The outermost shell is what we call the valence shell, and we have 4 valence electrons in the outermost shell. But we also showed that there are 8 possible electron states in the valence shell. So only 4 of the 8 possible electron states are occupied. So if you take a look at the solid structure of silicon, so this is a 2-dimensional representation of a solid silicon structure. It is actually 3-dimensional. It is tetrahedral, as I mentioned last time. Each silicon atom shares a valence electron with one other silicon atom. So for example, this silicon atom, okay, this has originally 4 valence electrons, and it shares this with 4 other silicon atoms. So that's this one, this one, this one, and this one. Okay. And those atoms also share 1 valence electron with the original silicon atom. So from the perspective of this silicon atom, there are actually 8 electrons surrounding it. That occupies the 8 possible electron states. And all the silicon atoms have that perspective, that there are 8 electrons surrounding it, occupying the 8 possible electron states. And that's how the solid is formed. This is what bonds this is what bonds the atoms of the silicon together in a solid. Okay, then we talked about the energy band diagram. So you have what is called a conduction band. So here I marked that in yellow. And what is called a valence bond, and this is what I marked in light blue. Where E sub C is the minimum energy of a conducting electron, and E sub V is the maximum energy of a valence electron. At 0 degrees Kelvin, for a pure semiconductor, the valence bonds are all occupied, or the valence electron states are all occupied. So all your electrons are here. There is no electron here. This is at 0 degrees Kelvin. Now, if you raise the temperature higher than 0 degrees Kelvin, what happens? The electrons acquire energy. This is thermally acquired energy. So because of thermally acquired energy, it is possible for electrons to break from the covalent bond and jump to the conduction band. So I'm going to illustrate that this way. So let's say this electron, sorry. Okay, let's say this electron gains enough thermally acquired energy. What's going to happen? Okay. It's going to break away from the covalent bond and jump to the conduction band. That's what's going to happen. And what will be left here will be what we call a hole. So when an electron is promoted to the conduction band, what happens is an electron hole pair is formed. The formation of an electron hole pair. Okay. And what is the significance of having this electron hole pair? Well, if I have an electric field, for example, in this direction, so this is an electric field, no, not energy. So I distinguish between energy and electric field with the vector sign. If I have an electric field in this direction, what will happen? Now this electrons tend to move opposite the direction of an electric field. So this electron will move this way. Okay. Now these electrons are in the valence bond. They are tightly bound to the atom that they belong to. They will not have enough energy to just move around, no? Because they are here in the valence bond. No, they may not have enough energy to move around as this conduction electron will have. No, but it can have enough energy to jump from here. Sorry, no, I should draw another electron here. No, okay, I'm talking about this electron. No, this electron may not have enough energy, okay, to move around the way this conduction electron has, but this electron can have enough energy to jump from here to here, because here you have an empty energy state. So this electron can jump here, and what will happen now is, okay, this is now going to be my new hole. So now this is going to be occupied. There's going to be an electron here. And now here I have a new hole. So my hole has shifted from left to right, or my hole is moving in the direction of the electric field. In doing so, my hole is actually acting like a positive charge carrier. Why is it acting like a positive charge carrier? Okay, consider this silicon atom. Okay. This is neutral. In fact, this entire solid is neutral. Whatever number of positive charges contained in the nucleus, that would also be the number of electrons surrounding the nucleus. So this is neutral. Now, the minute I create a hole, so let's say this becomes a hole, no? Because the electron that used to occupy it is promoted into the conduction band. The minute I create a hole, this originally had enough positive charge, okay, to neutralize 4 electrons, but now there will only be 3 electrons around it. In effect, this atom becomes positively charged. This atom becomes positively charged. And as your hole moves around, so for example, if there's an electric field, maybe this electron will next jump to this hole. And then this is the new position of your hole. And then maybe this electron will jump to this hole, and this will be the new position of your hole. No? So as your hole moves around, the positive charge is moving. Because when this is your new hole, it is now this silicon atom which looks positively charged because there are not enough electrons around it to neutralize the number of positive charges in the nucleus. So the important takeaway here is your hole acts like a positive charge carrier. In the presence of an electric field, your hole will move in the direction of the electric field, And as your hole moves, the atom to which the hole belongs becomes net positively charged. And that's why it acts like a positive charge carrier. Is there any question with regard to that before I proceed? Any questions? Okay. Okay. And then I define the term intrinsic concentration. Intrinsic concentration is the number of conducting electrons present in an intrinsic semiconductor at a particular temperature. And for silicon, the value of your intrinsic concentration is 1.5 times 10 to the 10 electrons. This is an approximate value. 1.5 times 10 to the 10 electrons per centimeter cube. Okay, note that in the last lecture I gave a figure 1. In fact, I even showed you a graph of how intrinsic concentration varies with temperature. And if you take a look at that graph, and you can see that from the notes that I published of my lecture, it's actually greater than 1 if you try to interpolate that from the graph. Some books say 1 times 10 to the 10. The reference for this course, I just checked it. This is Cedra and Smith. That is the main reference for this course. Says it's about 1.5 times 10 to the 10. So let's use 1.5 times 10 to the 10. This is the intrinsic concentration. That is the number of conducting electrons present in an intrinsic semiconductor. Ano ibig sabihin ng intrinsic ulit? Anyone? Shout out. What do we mean by intrinsic?
Pure.
That's right, no, John? A pure semiconductor at a particular temperature. No? So at room temperature, 1.5 times 10 to the 10 ang gagamitin natin. Now, if we say N is our electron concentration, by the way, no, whenever I say electron concentration, it is implied that these are free electrons or conducting electrons. Hindi natin sinasama dito yung bound electrons na nasa valence band. No? So if N is my electron concentration and P is my hole concentration, then for pure silicon, N will be equal to P because every time you create a free electron, you also create a hole. Remember what I said here? You always form an electron-hole pair. No? When you have an electron that is promoted to the conduction band, automatically you get a hole here. So N will be equal to P, and that will be equal to Ni, your intrinsic concentration. Okay, note that silicon has this number of atoms per centimeter cubed. It has 5 times 10 to the 22 atoms per centimeter cubed. That means that there is only one electron-hole pair generated at room temperature for every 3.3 times 10 to the 12 atoms. That's how few, ganyang kaliit yung mga electrons na napopromote to the conduction band at room temperature. 1 for every 3.3 times 10 to the 12 atoms. So I'm just throwing these numbers out. That's just to give you an appreciation of how small your intrinsic concentration is compared to the total number of atoms in your silicon. Okay. Okay, I'll talk now about extrinsic semiconductors. Okay, when we talk about extrinsic semiconductors, here impurities are added to enhance the electrical properties of the semiconductor. So we have our intrinsic semiconductor, which is pure. We add impurities to enhance the electrical property. And after adding impurities, okay, we now call the semiconductors having been doped. So extrinsic semiconductors are also called doped semiconductors. And there are various ways of doing this. If you take a look at your notes, these are the notes published in UVLE, the published notes rather. It says there what are the different ways of doing this. You can do this through diffusion, through ion implantation. Those are some of the methods. Okay, there are two types of impurities. Okay. The first type we call acceptor impurities. And the second type we call donor impurities. Okay, so let's first discuss acceptor impurities. What are acceptor impurities? Acceptor impurities have three electrons in the valence band. So this would belong to group 3 of your periodic table, of the periodic table of elements. So examples of acceptor impurities: you have boron, you have aluminum, and you have gallium. Those are some of the common acceptor impurities that are used to dope intrinsic semiconductors. Now, what will happen? What will happen if you dope a semiconductor? The impurity atom will lodge itself in the crystal structure of the semiconductor. So, for example, dati-dati. Okay, I'll draw it again. No, this is your crystal structure. Okay, dati silicon lahat yan. And then you had your, okay, you had your shared electrons in your covalent bonds. Okay, the acceptor impurity will lodge itself into the crystal structure. So in business silicon, ito for example, magiging boron. Business silicon, magiging boron. But boron has only 3 electrons in the valence band, no? As opposed to silicon, which is 4. So, in fact, magiging kulang to. Magiging kulang to. This boron will only be able to share. This boron will only be able to share 3 electrons with 3 other silicon atoms. In other words, there's going to be a hole here. There will be a hole. Okay. So when you dope a silicon with an acceptor impurity, for every dope atom, for every impurity atom, you create 1 hole. Now, this is assuming that we have what is called total ionization. Total ionization means that all of the impurities end up being ionized. So you end up with 1 hole. Okay. Now, my question is this. What is the charge of this solid? Is it going to be positively charged, or is it going to be negatively charged, or is it going to be neutral? So 3 options. Okay. Positive, negative, or neutral. How many think it's going to be positive? I just want to see an indication. How many think it's going to be positive? Yeah, just raise your hand. Okay, how many think it's going to be negative? Well, meron pa rin? Wala. Nobody thinks it's going to be negative. Okay, the answer is it's going to be neutral. Okay, this is still going to be neutral. Why? No? This boron atom would have the equivalent of well, it has three electrons in the valence shell. No? So it will have the equivalent of three electron charges in its nucleus. Positive electron charges in its nucleus. No? So this boron atom will be neutral, right? Because kung tatlo yung electrons siya sa valence band, it will have a corresponding number of positive charges in its nucleus. And all the other atoms will also continue to be neutral, no? Because whatever number of atoms in the valence band will have a corresponding number of positive charge in the nucleus. So this stays electrically neutral. Okay. However, you have an empty energy level. You have an empty energy level. Now, if you take a look at the energy band diagram, okay, so we said that this is the conduction band and this is the valence band. So this is EC and this is EV. The energy level of this particular hole is going to be somewhere here. Okay, that's the energy level of the hole created by doping. Okay, we said that electrons here, so you have electrons here. So here you have a hole, no? You have a hole there. Electrons here will not have enough energy to jump, may not have enough energy to jump to the conduction band. But this, the energy level of this hole is actually very close to E sub V. So konting-konting energy lang yung kailangan for this electron to jump to this hole, no? So most likely this electron is going to jump there. And when that electron jumps there, this is now going to be your new hole. No? This will be your new hole. And then you now have the usual hole action. No? If, for example, if we have an electric field here, if we have an electric field this way, then this electron will tend to jump there, and then this will be your new hole, and then so forth. No, this electron will jump there, and this will be your new hole. That is if there's an electric field this way. So now you have the normal hole action in the presence of an electric field. So that is what this impurity does. Okay. Now, what is the donor impurity? I think you can already guess what the donor impurity is. Your donor impurity you have 5 valence electrons. Okay, so this is group 5 of your periodic table. So examples would be, for example, phosphorus, arsenic. No? Arsenic. These are examples of donor impurities. And if you take a look at the solid structure, okay, well, I'm not going to draw it anymore. No, I'm not going to draw it anymore, but that's in the notes. But now, okay, so if this is your phosphorus, so it shares an electron with well, I ended up drawing it. No, sorry. No, so it shares an electron with 4 other silicon atoms this way. But after sharing 4 electrons, meron pa siyang isang extra. There's an extra electron. that there's an extra electron. That is after it manages to share 4 of its electrons. Okay. Now, again, this solid is going to be electrically neutral, because if this has 5 electrons in its outermost shell, then that means there's an equivalent charge, positive charge in its nucleus. So this is neutral. But the fact is, it will now have an extra electron. And if you take a look at the energy band diagram again, okay, so this is your valence band, this is your conduction band. Where is that? What is the energy level of that electron? It's going to be somewhere here. Okay, this is the energy level of the electron created by doping. So you have your electron here. It's very easy for this electron now to jump to the conduction band, because the energy level required for it to jump to the conduction band, maliit na lang, no? It's very easy to jump to the conduction band, and therefore now it can contribute to current. Okay, so that is your donor impurity. Okay, this type of semiconductor where you have acceptor impurities, you call this a p-type. And this type of semiconductor, you call this an n-type. Okay, again, a p-type semiconductor is electrically neutral. It is not positively charged. And an n-type semiconductor is electrically neutral. It is not negatively charged. It just so happens that a p-type semiconductor has holes available, and an n-type semiconductor has electrons available for purpose of conducting electricity. Now, what is the typical impurity concentration? In other words, how much impurities do we usually apply to the semiconductor? Well, typically, this is about 1 impurity. This is about 10 to the 15 impurities. This is typical, no? Per centimeter cube or per cubic centimeter. 10 to the 15 impurities per cubic centimeter. Now, if you recall, we said that silicon has 5 times 10 to the 22 atoms per cubic centimeter. What does that mean? This is 1 impurity. This translates to 1 impurity for every 5 times 10 to the 7 atoms. 5 times 10 to the 7 atoms. Or 1 impurity for every 50 million atoms. Okay, 1 impurity for every 50 million atoms. That impurity is not going to change the physical properties of the solid. So your physical properties of silicon, if this is silicon, will not change. Okay, if you take a look at an intrinsic semiconductor and an extrinsic semiconductor, a doped semiconductor, they will look the same, they will feel the same, they will taste the same, they will smell the same. That is because the extrinsic semiconductor will only have 1 impurity for every 50 million atoms. As a matter of fact, kung kayo si Atom Man, no? Imagine yourself being Atom Man and inserting yourself in the crystal, no? You might spend your entire lifetime trying to look for that single impurity, and you will never find it because there's only 1 for every 50 million atoms. It will look, feel, smell, taste the same. But the electrical properties will significantly change. However, your electrical properties will significantly change. Now, why is that so? Okay. So originally, no, let's say 300, let's say you're at 300 degrees Kelvin. So for an intrinsic semiconductor, at 300 degrees Kelvin, no, at 300 degrees Kelvin, okay, your electron concentration N will be approximately equal to 1.5 times 10 to the 10 per centimeter cubed. No? Okay. Now, this is my impurity concentration, 10 to the 15 impurities per centimeter cubed. No? So if we assume total ionization, I already told you what that is. Assume total ionization. Okay. If I have an N-type, that would give me an additional 5 times 10 to the 15 electrons, no? Additional 5 times 10 to the 15 electrons per centimeter cubed. This is assuming that each impurity will create one free electron. So what is the new value of N? The new value of N would be 1.5 times 10 to the 10. This is the original, plus 5 times 10 to the, not 5, no, just 10 to the 15 plus 10 to the 15, no? Which will actually be approximately equal to 10 to the 15 per centimeter cubed. If you compare 10 to the 15 with the original 1.5 times 10 to the 10, what is this? This is 66,000 times more free electrons. Your dope semiconductor would have 66,000 times more free electrons than your pure semiconductor. So while your physical properties do not change, it will look, smell, taste the same. The electrical properties will change significantly. Now, the value of your electron concentration now will be 66,000 times the original value. So this is going to create a vast change in the conductivity of your material. And that is what makes semiconductors great. By just adding a few impurities, you are able to greatly enhance the properties of your semiconductor, and this will not change its physical properties. Okay. Are there any questions? Okay, I'm going to talk about a sorry. I have to discuss this, no? Okay, for both intrinsic and extrinsic semiconductors, okay, the product of N and P is equal to Ni squared. No? The product of N and P is equal to Ni squared. This is what is called the mass action law. And actually, intuitively, it makes sense. For example, I have an intrinsic semiconductor, and then I dope it with donor impurities. So what will happen if I dope it with donor impurities? The number of electrons will increase. as the number of electrons increase, the probability that an electron will recombine with an existing hole will be greater. No, this is a process which we call recombination. Later on, in fact, in the notes, it talks about recombination. But recombination is when an electron loses energy and goes back to an empty energy state in the valence bond. No? That's what you call recombination. So when the number of electrons increase, the probability that the number of electrons that recombine with holes will increase, and therefore the number of holes will decrease. And it just so happens that the decrease in the number of holes will compensate for the increase in the number of electrons, so that the product of N and P will always be constant at Ni squared. We're not going to go through a derivation of that, so just take my word for it. If you're interested in a derivation, I think it's available in the references that we provided. So that's what we call the mass action law. Okay. Now remember that also recall that your semiconductor material, no, whether it be intrinsic or intrinsic, well, specifically if it's dope, no, the semiconductor material is neutral. Okay, so what does that mean? No? If I take the electron concentration, this is your number of electrons, number of free electrons. No? When we say electrons, number of free electrons existing, and these are negatively charged. And I add to that the number of acceptor impurities. Okay, when an acceptor, okay, this is your acceptor impurity, no? When a hole is occupied by an electron, so originally here I have a hole. When that is occupied by an electron, then all of a sudden this lattice position becomes negatively charged, because the boron atom has only enough positive charge to neutralize 3 electrons. Then now all of a sudden I'm adding an electron here, so this will become negatively charged. Okay, so if I get N and I add to that the number of acceptor electrons, that is my total number of negative charges per cubic centimeter. No? By the way, I forgot to later on I'll define it. No? Na, this is your acceptor impurity concentration. So this is the amount of negative charge. On the other hand, P is your number of holes. If you add to that the number of donors, so Nd is your donor impurity concentration. Then the number of negative charges should neutralize the number of positive charges. Okay, so you have this equation of electrical neutrality. And then you have another equation, which is your mass action law, which I just said here. Np is equal to Ni squared. Okay. So here, if Ni is a constant, because it is a constant at a particular temperature, we have 4 variables. Your variables are N and A, P and D. And if you know any 2 of the 4, you can compute for the other 2. No? I'll just repeat that here. No? N plus Na is equal to P plus Nd. Okay, and then Np is equal to Ni squared. Okay, so Ni is a constant at a fixed temperature. So knowing any two of N and A, P, and ND, you can solve for the other two. And I encourage students just to remember this, no? Because for example, in the notes, it gives you an equation how to solve for N, how to solve for P. Yeah. Yeah. In the notes, no. It gives you an equation how to solve for N, how to solve for P, and I don't like students actually memorizing equations, no. So all you have to do actually is remember these two. Okay, I think you have a formula N is equal to ND minus NA over 2 plus the square root of, and then there's such and such. That can be derived from these two, no? And then you can also have simplifying assumptions. No? For example, if ND is very much greater than N, and this will be true for um, a N-type semiconductor, no? Then N will just be approximately equal to ND. And if NA is very much greater than P, then P will just be approximately equal to NA. So those are your simplifying assumptions. Okay, the other thing that I want to introduce, which I think is important, is the Fermi function. Okay, the Fermi function, this is f of E. E here is energy, not electric field. Okay, this is the probability of energy state with energy E, that is if existent. I'll explain what I mean by if existent later on. Is occupied by an electron. The probability that an energy state with energy E, if existent, is occupied by an electron. Actually, there's a formula for the Fermi function. At this point, you don't have to remember it, but if you take a look at books, the Fermi function is something like this: 1/1 plus E minus P of F all over KT, where K is Boltzmann's constant and T is your temperature in degrees Kelvin. K is Boltzmann's constant, and T is your temperature in degrees Kelvin. And EF is what we call the Fermi energy level. The Fermi energy level. Okay, but yeah, you don't have to. I don't think we're going to give problems where you're going to have to apply this formula. No? Okay, let me plot the Fermi function. Here, I'm going to show the energy E, and here I'm going to show f of E. So here, this is a probability, f of E, and here, this is the energy, the energy level E. Okay, I'm going to show also here E sub C, This is going to be E sub C, and this is going to be E sub V. At at lo- at 0 degrees Kelvin, the plot of your Fermi function is going to look like this. Where this value is 1. So this is the plot at 0 degrees Kelvin. Okay, what is the significance of this plot? At 0 degrees Kelvin, the probability that electrons exist, no, with the energy states lower than EV will be 1. That is because all of your valence electrons here are occupied. And the probability that electrons exist in the conduction state will be 0. We said that at 0 degrees Kelvin, your semiconductor, your intrinsic semiconductor, this is an intrinsic semiconductor. Let me mention that. This is for an intrinsic semiconductor. Okay. For an intrinsic semiconductor, at 0 degrees Kelvin, all your valence electron states are occupied. That's why your probability is 1. And none of your electrons will be in the conduction band, and that's why your probability here is 0. Now remember that this is your forbidden band. So from here to here, this is your forbidden band. There are no actual energy states between here and here. No? So yun yung ibig sabihin ng if existent. So there's going to be a value for the Fermi function for energy states from here to here, for example, in fact, from here to here, but actually in reality, there are no existing states there. So we can disregard that. So we're really only talking about here, below EV, and here above EC. Okay, what happens when we raise the temperature? Okay, when we raise the temperature, this is what's going to happen. Let me use a different color. My plot is going to look this way. So this is a temperature greater than 0 degrees Kelvin. And this inflection point is going to be 1/2. In other words, we can define the Fermi energy E of F is the probability or is the energy where the probability that that energy level is occupied is 1/2. If I further raise the temperature, this is what my plot is going to look like. Okay. So this is a T now, let's say much greater than 0 degrees Kelvin. That's what my plot is going to look like. If you take a look now at this plot, take note here, at this point, the probability that your electron can exist is no longer equal to 0. So here, it is now possible for electrons to exist. Although the probability is still very small, but it is possible for electrons to exist. Now, when does that happen? That happens when your electron gains enough thermal energy to be promoted. And when that happens, you also have a corresponding number of holes now here. So this now represents your holes. Okay, because now the probability that this energy level is occupied is no longer equal to 1. It is now less than 1. And therefore, it's possible now for you to have holes here. Okay. What happens when you have a doped semiconductor? If you have an N-type semiconductor, okay, we will call this now EI, where EI is your intrinsic Fermi level. Okay, if you have an N-type semiconductor, what happens is your Fermi energy or your Fermi level is pushed up. This becomes your new Fermi energy. That is the probability that that's when the probability becomes equal to 1/2. No? So if you take a look, if this is 1, this is equal to 1/2. Okay, at 0 degrees Kelvin, of course you're going to see again this one, but at a particular temperature, you're going to see this. And here you now have more holes, more electrons. Your Fermi energy went up, and now you have more electrons. But notice you still don't have any holes. Here you have no holes. Okay. And if you have a p-type, the opposite happens. So this is now your EI, your intrinsic Fermi level. Your Fermi energy goes down. So if this is 1, okay, this is 1/2. Okay. At a temperature greater than 0 degrees, this is what this might look like. And now you have more holes. Okay, the reason why we introduce this concept is because later on, the Fermi energies are going to help you visualize how electrons or how charge carriers behave inside your solid. And how, for example, when you form a junction, the Fermi levels will have to align between the left and the right. Now, just a note, in a solid state device, you can only have one value of each of F. In a solid state device, you can only have one value of each of F. Okay, I don't think I'll have time to finish up the material, so I'm going to go very quickly from now, no? Because supposedly this is still part of 1A, no? Module 1A. Okay, so yung module 1B is supposed to cover conduction mechanisms in semiconductors. And there are three mechanisms that are taken up. These are in your notes. The first is what we call drift. The second is what we call diffusion. And the third is recombination generation. Generation. So I'll just very briefly touch on the three. So we'll start with drift. What is drift? No, drift is the tendency of charges to move in the presence of an electric field. When you have an electric field, your charges will tend to move. If I have an electric field in this direction, okay, then my electron will tend to move this way, okay, and then I'll call it a hole. No? My hole will tend to move that way. I already told you, no, it's not actually your hole moving, but these are electrons moving, creating new holes. But the net effect is like your hole is moving. And then the velocity of movement this is going to be proportional to the magnitude of your electric field, no? Proportional to the electric field intensity. In fact, V, this is velocity, is going to be equal to mu times E, where mu is what we call the mobility of the charge. Now, you might get the impression that the movement is always in a straight line. For example, if I have an electron, and then this is my electric field, you might get the impression that this electron will always move in a straight line. Actually, that is not the case. When an electron moves, it will encounter obstacles. There are many possible obstacles. For example, it might encounter other electrons. It might encounter the nuclei of the atoms, and so it will actually move in a jagged manner. So the actual movement might be this way, no? But still there will be a net movement. There will be a net movement, and this is actually a net velocity. It's a net velocity. So that is equal to mu times E, where mu is the mobility of the charge. Now let's take a look at charges per se. Let's say I have a conductor or a solid. Let's say it's cylindrical in shape. Okay, and then I have a cross-sectional area A, and these are my charges that are moving. Okay, we know from EEE 123 that your current I is equal to the rate of change of charge with respect to time. I is equal to dq dt, where q is the amount of charge that is moving across your cross-sectional area. And we define charge density, J. This is defined as your current density, not charge density. Current density. This will just be equal to I over A. Your current density is equal to I over A. So J, your current density, is equal to, by the way, current density is current per cross-sectional area, or current, for example, per square centimeter, current per cross-sectional area. So J will be 1 over A dq by dt. Now, what is Q? Q, this is the amount of charge. Okay. is equal to the value of the charge Q. No? Let's say for electrons, no? Let's say amount, Q is amount of charge. No? So let's say for electrons, okay, Q is equal to the value of the charge, small letter q, multiplied by your electron concentration, multiplied by your cross-sectional area. Okay. Multiplied, well, yeah. No, sorry, let me go through that again. Yeah. Multiplied by the length. So for example, let's say we're considering this volume. We're considering this volume. So let's say this is X. So multiplied by X. So again, what is Q? Q is your amount of charge. That's the coulombs per charge, number of coulombs per charge. So we know that, for example, Q for an electron is equal to minus 1.6 times 10 to the minus 19 coulombs. That is for an electron. So Q is the value of your charge. And this is your electron concentration. This is the number of electrons per cubic centimeter. Okay, so you have to multiply N by the volume, by the number of cubic centimeters, to be able to get the total number of electrons in that particular volume. And then if you multiply that by Q, you're going to get your total charge. Now, what is your volume? Your volume is your cross-sectional area multiplied by X. And therefore, dq dt, what is dq dt? Will just now be equal to Q and A dx by dt. No, but what is dx by dt? Dx by dt is actually your velocity. So this is just Q and A. Okay. And what is your velocity? Here we said velocity is mu times E. Now we're going to distinguish it by saying muse of n. So muse of n, this is the mobility of electrons. Because here, we just said the mobility of the charge. So if it's an electron, we say muse of n. If it's a hole, we say muse of p. So that is dq dt. So this is equal to I. This is your current due to electrons. Okay. For holes, you can do the same thing, assuming now this is holes. Okay. Your dq dt, okay, is equal to q p muse of p. Sorry, I'm missing something. I forgot the E. No, E. Muse of P, E. Okay, this is your current due to holes. Okay, your current due to electrons, your current flowing due to electrons will be opposite the current flowing due to holes. But the charge of an electron is negative, and therefore the negative of the opposite direction becomes positive. That's why the sign of your current due to electrons and the sign of your current due to holes will both be positive, because in your current due to electrons, negative yung charge mo, pero negative din yung direction of flow. So negative nagiging positive. This is IN. This is your current due to electrons. We call this due to drift. No? And then this is your I due to holes. We call it due to drift. No. J is equal to I over A. So we already said that here. Sorry, where did we say that? Here pala, no? J is equal to I over A. Okay. So J due to drift, no, will just be equal to Jn due to drift plus Jp due to drift. Okay. So what is this going to be equal to? This is going to be Qn use of n plus Qp use of p multiplied by E. And this is now what we call sigma, which is your conductivity. So you have the formula. Actually, this is a vector, no? J is a vector. You have the formula J is equal to sigma E. Okay, where sigma is again Q and use of n, Q n use of n plus QP use of P. No? That's your sigma. And this is Ohm's law restated. So this is your conductivity. This is 1 over your resistivity. This is resistivity. So that's the first mechanism, drift. Okay, let's talk about diffusion. Diffusion is the tendency of a carrier concentration to be equal over a volume. And to illustrate diffusion, for example, what happens when, for example, if I have water, let's say this is water, I put a drop of ink. This is ink. Ano mangyayari, no? So the ink will fall into the water, and then you're going to see the ink diffuse. And at steady state, the ink would have spread uniformly in the water. That's at steady state. So that's to illustrate diffusion. It's a tendency of carrier concentration. If we think about the ink like electrons, for example, if you drop an electron in one part of your semiconductor, there's a tendency for those electrons, to spread itself over the entire volume until the electron concentration becomes equal throughout the entire volume. By the way, we're talking here, there is no electric field present. Not like in drift that there's an electric field present. Here, there's no electric field present. So we're just assuming. Well, later on, we're going to talk about thermal equilibrium, but we're just assuming there's no excitation. Okay, so yun yung idea ng diffusion. Let me give an example. If I have a semiconductor, Let's say this is my semiconductor. So let's say this is the x-axis. And let's say I manage to inject electrons here. No? This is injected electrons. Okay, now how do I manage to do that? Well, you're going to study that later on, no? How you do charge injection. But for example, one way of me injecting electrons here is by, for example, just this particular surface, I might introduce heat. No, that's one way. Okay, or another way is illumination, because illumination is another way of generating electron hole pairs. When you radiate a surface, you might impart enough energy to the electron due to radiation so that it will jump from the valence band to the conduction band. No? But for the meantime, just imagine that we are able to inject electrons in this particular surface. So if I take a look at the electron concentration here, it will be high. Let's say we continuously inject electrons. Now, what is going to be the profile? This is going to end up being this way. The profile is going to end up being this way. Okay. And so your electrons, these are your electrons, are actually moving to the right. If electrons are moving to the right, that means you have a current moving to the left, because current is opposite the direction of electron flow. So we have what we call a diffusion current. That is due to electrons. The current density due to the diffusion of electrons, I'll call that Jn diffusion, will be proportional to the rate of change of your concentration with respect to x. And in fact, your formula now is Jn diffusion is equal to Q d of n dn by dx, where dn by dx is the rate of change of the concentration. In other words, if the difference in concentration is very high, then your current is higher. If the difference in concentration is very low along the x, or the rate of change of concentration is very low, then your diffusion current is lower. Now this d of n, this is what we call the diffusion constant of electrons. Okay. Now for holes, it's going to be different. Actually, the same principle. Let's say I inject holes. I manage to inject holes. So I'm going to get a similar profile here. Let's say similar profile here. So my concentration of holes in the left is high, on the right is low. So your hole will move toward the right. And your diffusion current will be from left to right. Okay. Now the diffusion current is going to be proportional, okay, to negative dp by dx. Why? That's taking into consideration that the hole and the diffusion current are in the same direction. The hole and the diffusion current are in the same direction. And your formula will now be equal to minus q d of p dp by dx. Okay. So if you get your total diffusion So this is Jn diffusion plus Jp diffusion. So this takes into account the non-uniform concentration of both electrons and holes. Okay, this is Q dn by dx minus Q dp by dx. Now, if you have diffusion in the presence of an electric field, now you have your total current density, and that's going to be equal to your drift current density plus your diffusion current density. I'm going to stop there. I wanted to discuss certain things, like what happens if you have a non-uniformly doped semiconductor. Then there's going to be natural drift, and then there's going to be an electric field, and there's going to be certain things are going to happen, but I don't have time to do that anymore. And I don't think I will go into that next week, because we have new topics to discuss next week. So I'm going to leave it up to you to read up the notes, study the notes, and don't hesitate to ask questions. Do it, as I mentioned last time, do it through to Piazza. If you have any questions, do it through Piazza. And somebody's always monitoring that, and you can expect an answer to your question. Okay. Are there any questions now before I let go of you? Okay, it might be hard for you to keep up with me if you never took a look at the notes beforehand. Never took a look at the material beforehand. So my suggestion, as always, would be before you attend the synchronous consultation session, take a look at the notes already. In fact, if you already have questions, you don't even have to wait for me to get to that subject matter. You can ask it already, when during the session. Okay. Okay. So yeah, I'll close the session as soon as the last person leaves, just in case somebody wants to ask a question. So I'll just post my notes in uli. Nakita ba niyo yung notes na pinost ko last time? Yeah, I hope you did. Okay. So that's all. Thank you.
Thank you po, sir.
Thank you,
You're
sir.
welcome.
Thank you, sir.
Welcome.
Thank you, sir.
Thank you, sir.